Hello guys, today in this video we'll be looking at the Bellman-Ford algorithm of Computer Networks Laboratory. So firstly we'll solve a problem of Bellman-Ford algorithm. So Bellman-Ford algorithm is applied for a graph to find out the shortest distance, single source shortest distance, that is from a source. Suppose we take the source vertex to be as A. From A we find the shortest distance to all the other vertices in the graph. So here in this case, so we'll find the shortest distance between A to B, A to C and A to D. So in this graph there are 4 vertices, as you can see, A, B, C, D. So number of vertices is equal to 4 and number of edges is equal to again 4. Then we'll calculate the relaxation time, that is how many times you have to do the iterations. So relaxation time is equal to number of vertices minus 1. So here it will be 3. So you have to carry out the iterations for 3 times. So firstly list out all the edges in the graph, that is A to B, B to C, then you have B to D, then you have D to C. So these are the edges that you have found in the graph. After which you have to initialize the source vertex to be 0 and all the other vertices to be as infinity. Now we'll come to the edge A to B. Here first you will write down whatever is there on the source, the weight on the the source which you have initialized, that is 0, plus whatever distance between A to B, that is source to destination, that is 4, should be less than whatever the weight you have assigned to the initialization you've done to B, that is infinity. So you'll check this condition, that is 0 plus 4 is 4, so 4 is less than infinity. Sorry, 4 is less than infinity, yes, infinity is greater. That's why what you do is you update the infinity value that you have assigned to B as the distance value of calculated here, that is 4. Now we'll calculate with respect to B to C. Now coming to B to C, again whatever weight is on B, that is 4, plus the distance between B to C, that is 5, which is, this should be less than whatever weight on C that you have initialized, that is infinity. Yes, it's true, so you'll assign this to C, that is 4 plus 5 is 9. Now coming to B to D, again B weight is 4 plus the distance between B to D is 3, should be less than whatever is their initialized weight on D, that is infinity. Yes, it's true, that is 7, so you change this to 7. Now coming to D to C, D weight assigned, you have to update whatever you have been updated as here. So 7 plus the distance between D to C is 2, should be less than whatever is the weight you have assigned to C, that is 9. 9 less than 9, not possible, so you don't update anything. Now coming to the second iteration, again we'll go through A to B. A to B, that is weight on A plus distance between A to B should be less than whatever weight you have it on B. This is 4 less than 4, this is not true, so no updation. Then you come to B to C. B to C, weight on B plus B to C distance, that is 5, less than whatever weight on C, that is 9. 4 plus 5, 9 less than 9, not correct, so you don't update. Then B to D, the weight on B is 4 plus B to D distance is 3, and if it is you have to check if it is less than the weight that is assigned to D, that is initialized, so that is 7. 7 less than 7 is false, so you don't update. Coming to D to C, the weight on D plus distance between D to C and less than the weight that was initialized to C, that is 9. So 9 less than 9, it is not true, so you don't update. So once you get that all of the edges have not been updated, then the further iterations also goes on like this. Therefore you can just copy down the similar thing, that if you can do again, the iterations can be done again, the same answer you'll be getting. Therefore the shortest distance of A to A is 0, then shortest distance from A to B is 4, whatever the final value you'll get on the weights is the shortest distance. Then whatever the shortest distance between A to C is 9, and the shortest distance between A to D is 7. So this is how the Bellman-Ford algorithm works, and this is how the problem is solved. So we'll be taking up the program next. So coming to the program, first we'll look at the main program. So you have the public static void main and the string arguments that is passed. Then we'll declare a variable number of vertices that is assigned with 0. Then you'll declare a variable source. Then you have a scanner class and a scanner object defined to in order to get the input from the user. Then you ask the user to enter the number of vertices, and the user will use the scanner object and enter the number of vertices to the num vertex num underscore vr variable that you have specified. Then you'll specify an adjacency matrix, that is to give the input to the program, because the program doesn't understand how will you give the uh, graph as an input to the program. That is given through adjacency matrix. So you can represent the graph as an adjacency matrix. That is why we'll define an adjacency matrix A, and we'll specify the memory for it, number of vertices plus 1 and number of vertices plus 1, and you'll ask the user to enter the adjacency matrix. Then you'll run a for loop, two for loops, that is from source, and source less than or equals to number of vertices, and destination less than or equal to number of vertices, and this will be run. And you'll ask the user to enter for each of the rows and corresponding columns. And if you find that if the source and destination are equal, suppose say A to A, that means it is a self loop, then it will be like the adjacency matrix value will be equal to 0, and you continue. So next you will check if the source to destination adjacency in the adjacency matrix, that if it is equal to 0. Suppose they are not equal, Sn is not equal to Dn, it is not a self loop, but still they are equal to 0. That means that there is no direct connection between the two vertices. That is why we set it to maximum value, that is infinity. Then you ask the user to enter the source vertex, and the source vertex will be entered by the user using the scanner object. Then you have a object that is specified, BELLMANFORD B. This is the object you're specifying for the function BELLMANFORD, and you're passing the argument number of vertices. So this is where the function will be, that is public class BELLMANFORD, and it will have a variable D, that is an array which stores like the initial values that will be weighed upon the vertices. As we have done, the source vertex will be assigned as 0 and the other vertices to infinity. That is for this. To hold those values, we have this D array. Then you have number of vertices. Then you have the max value, that is, you can't specify infinity in program. That is why you specify it as triple line. Then you have public class public BELLMANFORD that you'll be calling in the main function, that will be passed with number of vertices, and you'll use this pointer pointer to point the number of vertices, that is you're pointing to this number of vertices in this function. Then you'll use this D array to assign the memory for it. So this is about the public BELLMANFORD. Now it will come back to the main function after finishing the function of public BELLMANFORD. So when it comes back to the main function after the BELLMANFORD function, it will use that object that was created and call the other function, that is BELLMANFORD evaluation, and pass the source vertex and the adjacency matrix that was given by the user. And this is for the scanner class. You'll be closing the scanner class that you have opened for the user to enter the values. So this is about the main function. So BELLMANFORD, when it's called BELLMANFORD evaluation, it goes to the BELLMANFORD evaluation function. So once it's called in the main function, it will come here, that is BELLMANFORD evaluation. It will be passed with the source and the adjacency matrix. Then you have the for loop, that is for each of the node, and it will iterate through all the number of vertices, and it will assign the nodes with infinity firstly, with all the nodes are assigned with infinity initially, that is the on top of it which we write in the program. The same thing happens here, but the D of source will be assigned to 0, as we assign the source value to be 0 and the others to be infinity. The same thing is done in the program also. Then it will run a for loop again with the node and the source. You have a for loop for the node and for loop for source, for loop for destination, and if the adjacency matrix does not have a like s, the distance between the source and destination not equal to infinity or triple line, then what you do is you'll check the condition. If distance if the distance of the destination node is greater than distance of the source node plus the distance between the adjacency matrix value of the distance between the source and the destination, as we do in the program. That is, suppose you have A and B. This is the destination, this is this source, and you have suppose value 7 and you have 5 between the distance between this, and you have 0 here. What you do is, here according to the distance of destination, that is 7 greater than distance of source. Here source is 0 plus distance between these two is 5. 7 is greater than 5. Yes, it's true. You have to change the value. You have to assign D of destination. That is, here you have to change the destination value, that is 7 will be changed to the lesser value, that is the sum of these two, that will be 5. The same thing what we do in program will be done here. Then you close the for loops. Then you again open the for loop for source. Also, you'll be opening a for loop for destination, and you'll check the same condition like you checked in the last if, that is the adjacency value for the source and destination should not be equal to infinity. Then you'll check the same condition, that is distance of destination should be greater than distance of source. If this is the case, distance of destination is greater than distance of source plus the adjacency value between the source and the destination. If the same, see, those iterations were done till the relaxation time, and after the relaxation time also, if the conditions fails to be as true, like it is implemented as true, then you will say that the graph contains negative cycle. What actually happens in Bellman-Ford is actually Dijkstra's algorithm is more versatile, but we use Bellman-Ford because of its advantageous nature of holding negative weights in the edges, and also it can hold negative edges, but it cannot hold negative cycles. That is, if there is a cycle, say suppose you have vertex A, vertex B, vertex C, and you have 4, 5 and minus 12. So this is a cycle. So when you add it, minus 12 plus 5 plus 4, you'll be getting it as minus 3. This shouldn't happen. You shouldn't get a negative value when there is a cycle, but you can have a negative edge. Say suppose it was only minus 2. So when you add 9 minus 2 is 7. So the cycle value would be a positive value and the edge value is negative. This could be acceptable. But if after the relaxation time also the same thing happens, that means there are negative cycle in the graph and we cannot go with the Bellman-Ford algorithm. So that is what is printed here. Then you'll have the shortest distance to be printed out. So you'll go from, so there after this you have the vertex variable to print the distance between each of the distance between the source and each of the vertices. So you have the print statement for that, and the vertex will run through the total number of vertices. So this is what happens Bellman-Ford algorithm. Thank you guys.